Today we're going to talk about the humble 2x4 and how that 2x4 might be used as a column. A 2x4 made of wood is probably one of the most common structural elements in our world. But that 2x4 is not actually 2 inches by 4 inches. It's in fact 1.5 inches by 3.5 inches because you had to pay for the saw that cut the thing. This 2x4 has a modulus of elasticity of 1000 KSI. That's a little bit conservative, some of them are a bit stiffer than that, but it's a good start if we're going to do buckling calculations. And for this video, we're not going to consider crushing of the column, but only buckling. And this particular column is going to buckle preferentially in the weaker direction. So when we load a similar rubber model, we'll notice that the weak direction is the direction where I is lower, or where 1/12 BH cubed results in a lower value. So if I, in the strong direction, is equal to 1/12 BH cubed, that's going to be equal to 1/12 of 1.5 inches times 3.5 inches squared, giving me a value of, and I pre-calculated some of this stuff, that's going to give me 5.36 inches to the fourth. And that's going to be if the object tries to buckle this way. In the other direction, we're going to swap that 3.5 and 1.5 inch and get our weak direction stiffness, shape stiffness this is, 1/12 B cubed H, and that's going to give me 1/12 of 1.5 cubed times 3.5. And in the weak direction, it's dramatically weaker, and we get 0.98 inches to the fourth, or less than 1/5 of the shape stiffness. Now the material stiffness remains the same in both directions. So if I were to compute what the capacity of the column is, I would go back to my Euler buckling equation of P critical is equal to pi squared times the material stiffness times the shape stiffness divided by the length, the effective length squared. We're not going to go after end conditions in this video, and so we'll just say, hey, our length is that 8 foot. Many 2x4s come in a standard 8 foot length, so we're going to say, hey, I'm going to use that 8 foot length inside of here. But that means I've got to reconcile my units. Here I've got inches and kips, here I have inches, and my length I stated in feet. And so if we wanted to find out P critical in the weak direction, because that's the way it's going to fail. If I load this thing up, it's going to fail in the weak direction. I'm going to get pi squared times 1000 KSI times 0.98 inches to the fourth. All of that divided by 8 feet times 12 inches per foot, quantity squared. And if I do all that, it ends up being about 1.05 kips in compression is the critical force necessary to cause buckling in the weak direction. Specifically, when I load it, it's going to buckle like that. So, how can I push this number up? We know that this number is roughly 1/5 of the capacity in the strong direction. So I can pick this up by bracing the column in the center. And which direction am I going to brace it? I'm going to brace it in the weak direction by grabbing hold of it right here with another structural member perhaps. And there's some other ways of doing it, but maybe I'm going to put a beam in there, or I'm going to put some sort of jack leg. Something is going to be restraining the beam from moving in the in that weak direction, and therefore making the buckled shape look like an S rather than half an S, right? So it's going to be a full sine wave rather than half a sine wave. So how do I calculate that? Well, the effective length of the beam, of the column, is cut in half. So that my P crit braced in that weak direction is pi squared times 1,000 KSI times I, 0.98 inches to the fourth. All that divided by 8 times 12 divided by 2. Where did I brace it? I braced it at the middle. So what's my effective length? My effective length is half of what it had been in the unbraced condition. And what do I get? Well, if I square this, I'm going to be 4 times as stiff. And 4 times as strong. And that strength is going to give me 4.2 kips in compression. So by adding a simple brace at the center of the column in the weak direction, I increased that to 4 times the strength. I'm still going to be a little bit less than the buckling in the strong direction, which if you want to run the calculations, the P critical in the strong direction is about 5.7 kips. But by adding this brace, I came close to matching the buckling strength in the weak direction and the buckling strength in the strong direction. It wouldn't make sense for me to brace this column in both directions, because if I did, I would still be forcing the first buckling mode to be in that weak direction at 4.2 kips. So if I jacked up the buckling load in the strong direction, it doesn't really help me out, because I'm going to buckle first in that weak direction. So hope that fills you in. If you want to take a look, there's a great example in Philpott. Here, I'll tell you which one. The example you want to take a look at in Philpott is example 16.3, and that's on page 701 of the edition I have. Okay, hope this helped you out, and good luck on the problem set.